Good afternoon, and welcome to today's Microwaves and RF webcast. Our topic today is analog beamforming. What is it, and how does it impact phased array radar and 5G? Sponsored by Peregrine Semiconductor. I'm Nancy Friedrich with Penton's Design Engineering and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow Help icon below the slides. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please, feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the Submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Now, let's meet today's speaker. Andrew Christie is a technical marketing manager at Peregrine Semiconductor, a leading fabless provider of high-performance integrated RF solutions. A 20-year RF industry veteran, Christie has held a variety of engineering management roles at companies including Sarantel, RFMD, and Tate Electronics. Andrew earned a bachelor's degree in electrical and electronic engineering from the University of Canterbury. He is based out of Peregrine Semiconductor's European office in the United Kingdom. Now let me turn things over to our presenter. Andrew, the floor is yours.
Hello, this is Andrew Christie, and I'd like to share Peregrine's perspective on analog beamforming. So for today's presentation, we're going to start with some background on beamforming and why we need beamforming, a short introduction on some of the basic theory behind beamforming, and a brief discussion of analog versus digital beamforming. The bulk of the presentation will be covering what is important for complex beamforming, and we're going to take two case studies: phased array radar requirements, which we will link with one of Peregrine's products, and beamforming for 5G communication systems, where we will look at the communications environment and how this drives the requirements for a beamformer. So starting with the basic introduction of why do we need beamforming. For the purposes of today's presentation, when we refer to beamforming, we're referring to forming and dynamic steering of a microwave or millimeter wave signal using an antenna array. So there are other ways in which we can steer a beam, but for the purposes of today's discussion, we're going to constrain it to this topic. And initially, we're going to focus on phased array radar and communication systems, but I'll briefly introduce some of the applications where beamforming is appropriate and why. So for phased array radar, there are many applications and new ones are being conceived all of the time. But in general terms, the broad range of applications are generally either scanning the sky or scanning from the sky. And this slide illustrates some novel applications of phased array radar. So on the top left, we have an example of phased array radar being used for low altitude, short range weather prediction. It's also used from the sky, typically from satellites on the top right, for environmental monitoring, monitoring fault lines, flooding, deforestation. One of the most common applications is the bottom left, where we see weather mapping, weather tracking for aircraft, so they can route around weather systems. There are some newer applications such as oil spill detection, again, either from a satellite vehicle or from an oil platform. Another application of beamforming is satellite terminals, and specifically in the case where we're looking for low-profile antennas that are capable of scanning the sky. So traditionally this would have been done with a tracking dish, as shown in this central picture. However, it's not applicable for low-profile situations. So for example, we have an aircraft which is traveling at high speed, we need something aerodynamic. A train, for example, needs to be able to go through tunnels where there will be a low clearance, and again, the roof of a vehicle where we have aerodynamic issues. So the solution here is a beamforming phased array. And the final example is terrestrial communications, and today we're going to talk a little bit about 5G and the unique requirements for 5G systems, millimeter wave 5G systems. And here we need beamforming to maximize the transmission efficiency. The path losses are significantly higher than lower frequencies, so this requires us to use a phased array system. In addition, the applications require either multiple users, so multiple beams to be formed to track individuals, or using multiple beams for one user, such as polarization diversity. An additional benefit of using beamforming is that as we get to higher data rates and higher data densities, we can create smaller cells much more efficiently. We can manage the energy on the cell boundaries so there's less interference and spillover across cell boundaries. So just to touch on a little bit of basic theory behind beamforming, for the purposes of this example, we're taking a very simple example where we have uniform increments between the antenna array elements. So what this diagram is showing is a series of antenna array elements spaced at even spacings of distance d, and you can see on the right hand side we can work out the incremental phase that's required based on the formula 2 pi of a lambda d sine theta. So what this is showing us is that the spacing of the antennas is wavelength dependent, and the phase increment is also proportional to the spacing of the antenna elements in an array. So this is a simple example. We can get much more complex examples where we have different phase increments between elements. And this leads to forming a wavefront as shown in this animation. So moving on to digital versus analog beamforming. In this diagram we're showing 3 different types of beamforming. This is perhaps slightly more focused towards communication systems than phased array radar, but the basic concept is the same. So I'll go through each one at a time. So if we take digital beamforming, the basic premise here with digital beamforming is we have a baseband processing unit that drives a series of RF channels, and each RF channel drives an individual antenna element. So this gives us the ultimate flexibility in our system. It allows us to configure we can combine channels to get additional gain, so we can get the array gain, or we can have a larger number of channels to talk to a larger number of users. The disadvantage is its higher power consumption because we need a lot of baseband processing. All of the beamforming is done in baseband. And each channel requires a complete RF path. So this is the perhaps highest performance solution, but the least efficient solution. And typically this is not practical for millimeter wave beamforming because the bandwidths of the information are too high. If we go to the other extreme, which is full analog beamforming, in this diagram we can see full analog beamforming. In this case, for each channel, the beamforming is provided in an analog fashion, so we have a phase shifter and some form of gain control driving each antenna element. This is somewhat pre-configured, so you can have multiple RF channels transmitting unique information, but you need completely separate RF paths and analog beamforming paths, and you have separate antenna arrays for each channel. So this system is less flexible, it's lower power, and it's more difficult to reconfigure for different requirements. The third approach is a hybrid of the two, and in this case, we base it around an analog beamforming approach, but we combine the signals at the output of the beamforming element so that each path is connected to multiple antenna elements. This gives us a hybrid approach where there is some flexibility and reconfigurability. We can, again, combine RF channels as we did in the digital case, or we can keep them separate. And it's a kind of a halfway house. The disadvantage is the combining after the beamforming element creates loss, so we have to compensate for this. So this has an additional power loss over analog beamforming. Another area or another possibility and opportunity that beamforming creates is distributed amplification. So what we do, as we show here, we have multiple PAs, and the benefit of having multiple power amplifiers is the output power of each element, each PA element, is much lower. So this leads to the possibility of increased integration, whereas for a traditional system you might have a high power amplifier and the beamforming element in a separate technology, different technologies. When we get to these more distributed amplification cases, the PA power becomes much lower and lends itself to integration of all functions in a single technology. And the final advantage is we have increased reliability. Distributing the phase shifting and amplification across a number of elements means if one element fails, we maintain performance, or we see a very minimal degradation in performance. So having covered some basic theory behind and some basic applications, I'm now going to turn to phased array radar and talk a little bit about the environment and how this environment leads to the requirements for a beamformer, and then show the example of how Peregrine approached this for the specific case of phased array. So if I take a simple example and we talk about some of the challenges, for the case where you might be trying to track an aircraft, the direction of the object is important. At the same time, we may see some interfering signals from perhaps another aircraft that's flying at the same time. So ideally, we would like to optimize the pointing accuracy of this radar, and at the same time, we would like to minimize them. We want to maximize the interference suppression or minimize the interference. How do we go about doing this? What matters from a beamformer's perspective? How does the beamformer contribute to this? So this study explores the impact of pointing and how we can improve the fine angle resolution. And in the basic concept is if we have too many side lobes, it creates clutter. And the clutter makes it more difficult for us to identify the wanted signal. So in the bottom left diagram, we can see the primary signal is at azimuth angle 0, so the center of the diagram. and then we see a series of side lobes decaying as we go further away from 0 degrees. And the diagram is showing the red trace is showing with some errors in the system, so an amplitude error and a phase error. And the blue is showing the ideal case. And what this is telling us is that in the case, in this example, where we have a small error variance in the range of 0.2 dBs and a phase error variance in the range of 5 degrees, we get a 2 to 3 dB increase in side lobe energy. So what this is saying is if we can improve the RMS amplitude and phase errors of our beamformer, then we will get improved pointing accuracy. Now turning to interference suppression, and in this example with a 64 element array, on the vertical axis we're looking at the depth of the notch, which is showing us the suppression that we're achieving. And if we look at this in the case where we're looking for suppression or a notch depth of somewhere between 50 and 60 dBs. In this example, we're considering only phase error. The three curves, the two dotted lines and the solid line are with different levels of amplitude error. So this is primarily dominated by the phase error. So what we can see is that it's desirable to keep the phase error below 2%, the maximum phase error below 2 degrees. So if we consider these areas, and then we start to consider how we would implement a solution, what I like to describe Peregrine's approach and our philosophy behind products for phased array. So using the example of the PE19601. So just briefly reviewing what we covered in the last few slides. What we're talking about here is we want to minimize the RMS phase and amplitude errors. Most X-band phased array systems have a broad frequency operation. They may operate at point locations across the band, but generally systems are designed with the capability of working over a broad range. Again, phase resolution is important and accurate amplitude control. And finally, we haven't touched on, but many of these systems are high dynamic range systems, so we want high linearity out of our beamformer. So the Peregrine approach to phased array beamformers, if we take the two key blocks, you can see at the top the phase shifter and at the bottom the attenuator. The Peregrine approach to the phase shifter is using a distributed phase shifter. So the basic architecture is based around having a coupler and a switched reactive load. And the benefits of this system are it's broadband, extremely repeatable, and we achieve the accuracy that we desired plus the high linearity. So this architecture is a very robust solution and addresses our primary requirements. For the attenuation block, Peregrine has a large amount of experience in developing step attenuators, and again we use a passive approach primarily for its repeatability, its accuracy, and its high linearity. So if we move on to how does this translate into performance, I'm just going to quickly show a few plots of the achieved results. So again, we're talking about broadband performance, and in this case we can see this is an example showing attenuation on the chart on the left, and we can see the vertical scale shows the attenuation, and we can see along the x-axis, if we look from about 6 gigahertz to about 15 gigahertz, we can see that we cover the attenuation responses are generally fairly flat, and they cover the range in excess of 30 dBs of attenuation over that entire range. The chart on the right is a slight deviation. This is looking at phase, and we use a slightly different approach with phase. Again, covering the same frequency range, 6 to 15 gigahertz. The single device will cover that entire range. Here we use additional phase bits to create additional fill-in And you can see our aim here is to cover the whole 360 degrees range over that frequency span, which we achieve. And in this case, we have overlap of some of the results because we intend to use a lookup table in the final result, because this gives the most broad frequency response and the best accuracy. So now if we move to translating this into accuracy, we talked about errors earlier and how critical attenuation and phase errors are. This is showing a result for the left-hand chart shows the RMS attenuation error over a frequency range of 8 to 12 gigahertz. You can see we achieve very consistent very low attenuation error. On the right-hand chart, the same frequency range, we're showing phase error. And this is using a series of lookup tables in 1 gigahertz spans on the right-hand chart. You can see that the phase error is extremely low, in most cases well below 1 degree of phase error. Moving on to linearity, so we said linearity was important for high dynamic range systems, and these two charts are showing input IP3 for the PE19601. The left-hand chart is showing over the entire attenuation range of the device. So we have an excess of 30 dB attenuation range, and the linearity is above 47 dBm. Similarly, across the entire phase shifter range, we're seeing very consistent and very high linearity. So we talked about consistency being important in the system, because this enables us to minimize or eliminate calibration. And what we have here is a study that Peregrine has completed where we took samples of dye across a wafer. And in this case, you can see the highlighted, there are 5 locations across the wafer. They're all numbered depending on their location. And if we consider for a start the device in the middle, device 1708, this we decided randomly to pick as our reference device. And what we've done is we've measured all of the devices relative to each other. We've calculated a lookup table based on device 1708, and then we've applied it to the remaining 4 devices. So if we look at these charts, this is showing the result. There is a straight line indicating the ideal result and a series of plots showing each individual device. So on the left we can see attenuation, and on the right we can see phase. And we can see that particularly for phase it's very close to a straight line. For attenuation, all of the parts, although they're not quite a straight line, they're very consistent and track each other very well. So now if we transition this into errors, we go to this slide. What we see here is now we're reporting RMS errors for all of the devices. So on the left-hand column we can see the device number, so 0810. The next column shows whether it is attenuation or phase error we're reporting. And as we move across, we can see there's a column that says corrected RMS error. So this is the ideal RMS error. And then the next column shows the RMS error using the 1708 lookup table, so the shared lookup table for all devices. The second from right column shows the delta in the result, and as you can see, the error delta is extremely small. So what we're saying is we can use the same lookup table across all devices on the wafer. So again, this just simplifies the implementations of the device in a system. Another area that we consider is for a broadband system such as phased array, what's the best way to add gain to the system? As it has a broad frequency range, we have to think about this carefully. So this study shows a series of blocks. On the right you can see in the grade color the PE19601, so our beamforming device. In front of it we can see, in this example, a gain block, and before this an LNA. The LNA is in the system already, so it would be the system LNA. The gain block, and the purpose of the gain block in this case is to offset the loss of the beamformer. The question here is, where is the best place to put the gain in the system to optimize noise figure and cascade IP3 or output P1dB? So we can see in this case the highlighted box at the bottom is showing the calculated cascade IP3, cascade noise figure, and cascade output P1dB. So this is where we have the gain block in front of the phase shifter and DSA. In the next example, case 2, we have it after the beamforming block. And the final case, we look at the possibility of what would happen if you put it partway through. Would there be any benefit in doing this? So the summary of the results shows that, as you would expect, putting the gain before the beamforming block, so before the block that has loss, gives the best noise figure. It gives a modest output P1dB. Putting the gain after the beamformer, we sacrifice some noise figure, but we get a superior P1dB. The gain in the middle, as we can see, is a compromise. We don't get the optimum solution. So the peregrine conclusion from all of this is we think it justifies the decision to leave the gain outside of the device. So this allows, in an application, different amplifiers to be chosen depending on the frequency of operation of the system. There's no benefit to putting gain inside the device. In fact, there's a disadvantage because it reduces the bandwidth of operation of the device. So, in summary, phased array radar systems, they're typically broad frequency range. So we're trying to address this by providing flexibility and consistency, and we're focused on phase and attenuation accuracy. Again, we believe that keeping the amplification outside the beamformer gives the most flexible solution, the most versatile solution. We're focused on linearity because, again, we believe this is very important for high dynamic range systems. So now I'm going to move on to beamforming for communication systems. And as mentioned earlier, we're going to focus on millimeter wave systems. And we'll start, so this is relating to 5G type systems, and we're going to start looking at the urban environment. And so what we're going to look at is what is the channel behavior and how does it affect beamforming, and what does this mean for the requirements of the beamforming block. So if we start by looking at the materials and the environment that we might face, this study shows surface losses and reflections at boundaries. So we can see in the top chart there are a series of highlighted blocks, and the highlighted blocks are the materials with the highest loss. And what we can see from this is that things like clear glass and internal partition walls only have modest loss. But when we start talking about tinted glass, brick, or multiple walls, then the loss is high. So this is typically saying that you might find tinted glass in the exterior of a building, likewise brick. But the other part which is interesting is that multiple walls, so even multiple internal partition walls, can have significant attenuation. The second part of the study is looking at reflective surfaces. So imagine you are inside a building and you are transmitting a signal, and what this study is showing is that most of the energy is reflected. So this is consistent with what we said above. There's high loss if you transmit towards a surface. The less energy is reflected from higher angles. So as we get more towards, as we get to higher angles, we see less signal continuing on, and little is coupled directly through the wall. So again, what we're going to find is most of our solid barriers within a building are the signals are not going to penetrate. We're mostly going to get reflections, and the most effective reflections are going to be those with a lower angle. So going one step further, how does the urban channel behave at millimetre wave frequencies? So what does it look like? What is the environment like? First, a short definition. So most often many people talk about intersymbol interference, or ISI, but a less common term, but a very useful term, is maximum delay spread. So the diagram here shows the received power versus time delay, and the maximum delay spread is the time at which the smallest useful signal is received. And the other way it's reported is as an RMS delay spread. So another way of looking at this is that delay spread gives us an indication of the amount of multipath activity in the channel. And typically the lowest delay spread signal is the direct path signal, particularly in a line of sight system. Why is this definition useful? The reason it's useful is if we look at this study on the left-hand side, we can see a series of plots. The blue trace is taken at 28 gigahertz for a line of sight system, and the green trace is taken at 28 gigahertz for a non-line of sight system. And what we can see here is that the delay spread for the line of sight system is greater than the non-line of sight system. Now this may seem counterintuitive at this point, but it's also notable that there is a significant amount of delay spread in both cases. And we'll come back to why the line of sight has larger delay spread in a subsequent slide. The second part of these findings are that, and this is probably intuitively much more apparent and obvious, if we combine multiple beams, then we have the possibility of extending the distance, or effectively the link margin or the signal strength of the system. So if we have multiple reflections, if we combine them in the right manner, we can improve the link margin, or we can improve the data throughput rate. So why is delay spread higher in a line of sight system? The reason for this is if we don't have proper pointing of the beam, then the direct signal is having to reflect off a faraway surface and then come back again. So to minimize the delay spread, we need to have the antennas pointing at the source and vice versa. So typically, taking the signal with the lowest delay spread will result in the best link margin. So summarizing all of this, multipath signals need careful management and selection. So we want to pick the one with the appropriate delay spread, or the one with the strongest signal. We have the possibility of improving link margin if we combine multiple beams. So this is feeding into the idea that not only is beamforming useful for the reasons we highlighted earlier, but in a multipath environment we can gain additional advantage. So this is another study looking at non-line of sight environment, and in this study, and this has some interesting findings, that if you look at this example, the two cases were tested. You can see on the top right is a base station with a scan range of approximately plus or minus 45 degrees. In the box on the left, there are two mobile station cases. In one case, the mobile station points towards the base station and scans and finds the ideal signal. In the other case, the mobile station points away from the base station. And on the top left plot, there are a series of locations labelled with letters A, B, C, etc. And what we can show is if we look at these two examples, case F and case E, that E and F have higher throughput when they're pointing away from the base station. So if you compare the plot on the bottom left, in that case the base station and the mobile station are pointing towards each other. On the case of the right, the mobile station is pointing away from the base station. And the reason that this is most likely occurring in these two cases is they have obscured views, so they need a reflection to get a strong signal, and it may also be influenced by the fact that anything coming from directly, there's multiple signals arriving around the same time in the direct path case, causing more intersymbol interference. So again, this makes it important to be able to select the direction of the signal that we receive. So if we translate this into an indoor communications environment, so as we discussed earlier, there will be many obstructions. There will be lots of partition walls of different types, and we will see some cases where we might have a line of sight application, so the transmitter is able to see directly to receiver 2, but more likely we're going to see non-line of sight cases, and we're going to be relying on multipath. But as we said, the angle is important, and the lower the angle, the better the reflection we get. So we're not going to see a huge number of reflections. Now if we move to the outdoor communications case, so this is considering a 5G system. In this case, we have access points on street corners. The diagrams on the right are showing a plan view of three different case studies where we have different distances between the access points, and the conditions here are going to be primarily line of sight. There will be some limited non-line of sight applications, but generally we're going to try and steer the base station antenna so it points directly towards the user equipment. So we talked about phased array radar. How do the requirements differ for 5G millimeter wave type communication systems from phased array? And the answer to this question is integration, cost, size are key for 5G. As we showed on the previous slide, we're talking about putting access points at a very regular spacing, 100 meters apart, 50 meters apart, and so we need to make them low cost. They're much lower to transmit power, so it's well suited to integration, which also assists us with cost and size. Minimizing test and calibration are critical to managing the cost of the devices, and high dynamic range is less important because we're talking about a relatively short range link. So the attributes that we would require for a 5G beamformer would be something like this. Again, highly integrated solution, fast scanning. We have to track the user. So the user will be mobile in many cases, either walking or potentially in a vehicle. We need fine phase resolution so we can track the optimal signal. We minimize the delay spread. Pre-stored algorithms would be helpful in this case because this would help us with fast scanning. Less programming allows us to reconfigure the unit much faster. Multiple TXRU support. So this is going back to the idea that we may want more than one channel, either to track more than one user or to enable things like dual polarization, which give us link margin gains or data rate benefits. So again, looking at this, the Peregrine approach is it's a lower power system. The power requirement may be plus 12 to plus 17 dBm peak power per path. It's a fixed frequency system, so it's a relatively narrow fractional bandwidth, something in the order of maximum 1 gigahertz at 28 gigahertz. So all of this lends itself to much higher levels of integration. And the diagram at the bottom shows the type of integration that is possible and achievable with a technology such as ultra CMOS. We can see that the key beamforming element is shown at the center of the diagram towards the right as a phase shifter element. So that's the primary beamforming element. That beamforming element is driving a series of amplifiers which then drive the antenna array elements. So again, phase, calibration and accuracy are extremely important, as we discussed before. And this is showing some measured data of what is possible. And what we're showing in the top diagram is if we look across all phase possibilities, all combinations, looking at gain adjustment and phase adjustment, we can hold less than plus or minus 3 degrees phase error across all possible combinations. The diagram at the bottom is showing the calibration mapping for all states. So what this is showing is with gain control on the vertical axis and phase adjustment on the horizontal axis, the red dots indicate the ideal or target location for each point, and the blue dots show the measured results. So in most of the cases, we can see, particularly for the top 20 dBs of gain adjustment, we are very close to being on top of the ideal targets. So again, this is showing the capability of Peregrine's technology to develop very high performance, simple to calibrate, repeatable beamforming elements for millimeter waves. So in summary, we have optimized unique solutions. So we have optimized a solution for phased array radar, and we have an alternative optimized solution for communication systems. For phased array applications, where it's a broad frequency range, we focus on linearity, dynamic range, and the optimum solution is to leave the amplifier out of the beamformer. For millimeter wave communication systems like 5G, where integration is important, and the bandwidth is lower, the power levels are lower, and the size of the implementation is important. This integrated solution will be combine much more functionality into a single RFIC is the right approach. Thank you.
Thank you, Andrew, for that excellent presentation. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, simply type your question into the question window on the side of your screen and hit the Submit button. While we're answering your questions, please complete the feedback form, which is located on the bottom of your screen. Okay, our first question is, what semiconductor process is being used for 28 gigahertz power amplifiers? The 28 gigahertz, I assume.
So for 28 gigahertz, we're using Peregrine's Ultra CMOS process. For this application, it's a SOI process, so a CMOS on insulator process.
Thank you, Andrew. The next question is, does the attenuation change with the phase shift change in the PE 19601?
So that's a good question. There is some element of interaction between the two parameters. The behavior is quite linear, and if you would care to contact us separately, then we can share some information. It's relatively easy to compensate for that interaction because it is repeatable and linear.
Wonderful. Okay, thank you. We have another couple of questions actually around that same product. So the next one is the data sheet for the 19601 says it covers 6 to 12 gigahertz. Can the device be used at up to 15 gigahertz operation, as shown in your presentation?
So yes, the device can be used up to 15 gigahertz. We typically don't specify it over that entire range in the data sheets, but again, if you would like to contact us, we can give you inputs and insights into how the part operates at 15 gigahertz.
Perfect. Okay, thank you. The next question on that part is whether the PE19601 is an analog phase shifter.
Okay. So if I understand the question correctly, when you say analog, the person is asking if it's analog. I'm assuming they mean continuous analog phase shifter. The approach that we're using is we target having phase steps of approximately 5 degrees. So it's using a digital control structure and having discrete steps of phase.
I would think that would answer it, but folks, if there's any continuation or you want to revise or ask another detail, please, again, feel free to keep submitting questions. Okay, Andrew, the next one is, why do you get higher throughput in the non-line of sight indoor study when the mobile station is pointing away from the base station?
Okay, so I think we tried to explain that during the slide, but I think there's a couple of factors that are influencing this. One, it's non-line of sight, so there's not a perfectly clear view of the base station. So any signals that are coming directly from the direction of the base station are reflecting off surfaces before they arrive at the device. And if you look at the number of, there's poles and other obstructions in the way, and there's a number of them that are close to equally spaced, which is probably resulting in a number of signals arriving in the direct direction around the same time and causing increased inter-symbol interference. Whereas it's likely that there's a predominant reflected signal that is arriving at its own time.
Thank you, Andrew. This next question is a little bit definitely related to the previous one. It is, why does the line of sight case have a higher delay spread than the non-line of sight case?
Okay, so we discussed this also a little bit during the presentation. The reason for this is an error in the pointing between the source and the receiver. So if there's an error in the pointing between the transmitter and the receiver, then the direct path signal will not be received and will end up reflecting off a faraway surface and then coming back. So that's what creates the larger delay spread.
Thank you for that explanation. Okay, our next question is, can gain be added to the phased array beamformer? So
yes, in the case of the phased array, yes, gain could be added to the device, and the reason we didn't do this was because we believe it narrows the frequency response of the part and makes it much more restricted. The second reason we didn't do this is because in the phased array case, there's typically gain in other functional blocks. So typically there's a power amplifier after the part, and it seems more appropriate to partition the system and put the gain all in one active circuit block and have our part more versatile, broader frequency range, and optimized for its purpose, which is adjusting phase and attenuation.
Mm-hmm. Okay, great. We have another question from someone named Bob. He wants to know, what semiconductor technology is this in?
So all of Peregrine's products are in a proprietary SOI process. So we have a number of different versions of this. Some of these are silicon on insulators, some of them are silicon on sapphire. It's a CMOS process running on these substrates.
Excellent. Okay, and I'm going to ask the next one from someone named Theodore. He wants to know if there's any plan to develop a 5G RFIC for the 39 gigahertz range. So
I guess we would suggest that you contact us and we can discuss further.
That's a good answer. Okay. The next one is, does the antenna and the path to the antenna need to be accounted for proper beam forming?
So I think that depends. I think yes, it does in principle. The reason it would be important would be if there were different length paths with different delays between the output of the beamforming array and the antenna array. So if each antenna element had a different length path, that would need to be corrected for somewhere in the system.
Thank you. Okay, on a connected note, can you explain why the 28 gigahertz phase mapping and or calibration is important?
Okay, so I think this links up to one of the questions from earlier regarding the 19601. So typically you may see an interaction between the phase shifter and the attenuator. So when one is changed, it creates a small change in the other. And what we're showing with that diagram is when you use the correct mapping, which is what that plot, that series of plots are showing, you can remove that interaction. And because our parts are so consistent, we can provide a mapping that will, as you could see from the error, which was very small, so less than plus or minus 3 degrees, that we can achieve a very tight phase and attenuation control over the whole range of both.
Okay, thank you for that explanation. The next question, let's see, can you provide some details as to the modulation format used for the indoor communications environment tests?
So I would need to refer the person to the reference, which will be published with the, that wasn't a study that we did, that was a study that was prepared by, I think it was from memory, it's in the references, but New York University. So I don't recall what modulation format they used.
Okay. So we're getting close to the point where we have to tie things up. And folks, if we didn't get to your questions, we will make sure that they're passed on to Andrew and the rest of the Peregrine team. And I'm sure you'll be receiving answers from them. But in the meantime, Andrew, can you tell us, is there some additional information anywhere on some of the topics you covered today that you could refer people to?
Well, I think I would refer them to, there are a number of references which are highlighted in the presentation. So for some of the studies, those were based on academic reports and papers. So I would encourage people to take a look at those if they have more detailed questions. If they have questions in relation to our parts and our plans or our roadmaps, then if they would like to contact Peregrine, then we'd be very happy to discuss further.
Wonderful. Okay, well, this concludes today's presentation. On behalf of Microwaves and RF, I'd like to thank Peregrine Semiconductor for sponsoring today's event, Andrew for the great and very valuable presentation, and of course, all of you for joining. I hope you have a great remainder of your day.